Hello, welcome to Algebra with Doug. It's nice to see you again. We'll get started in a minute. There may still be people coming into the class, so I won't start with the math really super fast, but I'll do my usual thing. This is my Brazil jersey. Oh, the microphone clip popped off, so I'll fix that. That's always interesting to watch people do. I think that'll be okay. Let's hope. Okay, yes, it's my Brazil jersey, and there's not much to say about Brazil. We know they're good at soccer. It's very dusty. It is chalk dust. I have been wearing this all day. Mocha is upstairs. We have guests, and Mocha will not want to be down here with me because she thinks she's alone with me when she's down here while I'm doing this. She doesn't realize that there are sometimes hundreds of you with us. Dogs and technology. I really have to buy her a book or something. Okay, now we're getting into the algebra. We did some very basic algebra skills. We did a lot of them last week. And we did go into some problems where there's more than one step like this one. So this is a one-step algebra. That's a two-step algebra. What we want to do this week is lots and lots of extra practice, especially with the two-step algebra. But because I'm Doug, I want to start with an easier one, because I think it's always best to start a lesson with something really, really small and let people get their head into math mode. Math mode, that's what I call it. It's a useful mode to be in this world. Okay, so here we have x plus 4 equals 10. We know the basic idea of algebra. X is a number, but we don't know what it is. It's having a 4 added to it. We don't want that 4 there. We want our x to be alone. We want to isolate the x on one side of the equal sign. It doesn't even matter which side. We just want it to be alone. But right now it's having a 4 added to it, and we want to get rid of that 4. So what do? The opposite of adding a 4 is subtracting a 4. So we subtract a 4. But if we're going to subtract the 4 on the left side, we have to subtract the 4 on the right side. These are just the basic ideas of algebra, but they're so important. And I teach students, some of my students are 18 years old, they're 28 years old, and they didn't really learn this correctly back when they were beginning with their algebra, and they're just all confused all the time. But when you know to get rid of this 4, I do the opposite. It's being added, so I do the opposite, which is subtraction, and then these will cancel. That means my x is alone. 10 minus 4 is 6, so I have my answer. And I can verify my answer. I can say, well, if x is 6, 6 plus 4 equals 10. Yes, that verifies it. Such a quick one that I don't really have to write it down. I can just see that it's going to verify. So that is the most basic type of algebra problem, because there was really only one step here. We have similar steps when we are subtracting a 4, or when we're multiplying by a 4, or we're dividing by a 4. But we did cover all of those last week, and we are going to cover them this week, because when we move on to this two-step algebra problems, we have to deal with all 4 of those operations: addition, subtraction, multiplication, division. So we'll get plenty of practice with all of them. Now, I didn't leave myself very much room for this, and today I'm going to try to only put one problem at a time so that I can write nice and big. But I wanted to just be able to point at both of these at once, so we can see here's the one-step algebra, but here's a very similar looking two-step algebra. Now, of course, if you are able to type into the chat, definitely do so. If you know of an answer, you can type in your answer. And if you want to suggest an algebra problem, you can do that. I may choose one. I'm not sure. I have a bunch of good ones chosen, and I want to be careful not to choose anything that's too tricky. But I like to look at the chat and see if anything's coming in, how people are feeling. I like this. And I like it when students participate in the class. Just watching a teacher isn't as good for the brain learning as helping the teacher to make everybody learn. Helping everybody to learn, helping the teacher do his job. I might be sounding a little bit like I'm looking for a shortcut myself there. But no, when students participate, that's a better class. It's more lively. 2x plus 4 equals 10. This is our first two-step algebra that we're looking at. We have an x that has 2 numbers with it. It's multiplied by a 2, and it has a 4 added to it. We want to get both of those numbers away from the x so it can be alone. What do I do first? The first thing I do is I'm going to deal with this 4. So I'm just keeping the 2x. And how do I deal with this 4? The same way I did up here. If I'm adding a 4 to my x, or my term that includes x, and I want that 4 to go away, I do the opposite. I subtract the 4. But I have to do that on both sides. These cancel. Now I have 2x equals, and 10 minus 4 equals 6. We're not finished. I don't have room to finish. 2x equals 6. So I am copying this up here so I have a bit more room to finish it off. 2x equals 6. What do? My f is being multiplied by a 2. I want to do the opposite of multiplying by a 2, which is to divide by a 2. And I divide both sides by a 2. These cancel. My x is alone. It's x is equal to 3, and I can verify, just like I could in the first one. 2 times 3, that's 6. 6 plus 4 equals 10. It verifies as well. So the two-step algebra takes a little bit more paper or chalkboard wall, but it still is just as easy as the one-step algebra, because when you're doing your algebra, you only do one step at a time. And if you want to try to do more than one step at a time, you're kind of asking for it. I like to use a little bit of real estate on my paper when I'm doing multiple step problems, so that I have room to do things one thing at a time so that I can be careful. And that pays off. Now I'm going to erase these with a brand new clean microfiber cloth. So let's get the chalkboard wall nice and clean. And as always, when the teacher's erasing and writing, the students should be able to have a stretch or have a sip of water or do a little bit of exercise or something like that, so that you don't get a cramp from sitting too still in a math class for too long. Okay, now I wanted to try writing something else. I'm looking for next. I'm just going to create a new example. So very similar to that last one, 2x plus 4 equals 10. But I won't choose the exact same one. So how about 3x plus 1 equals 7? Okay, so it's not any more difficult. It is a two-step algebra. But the reason I wanted to put this up isn't necessarily to solve this one. It's to talk about how many different ways an algebra equation can look. Because you might think, okay, well, I learned the trick. It's the same old thing. I'm just doing the same thing over and over again. But it's amazing how different that same old thing can be. Let's see how many different ways we can make this look different. I can say, well, I can try 3x minus 1 equals 7. So I'm not showing a step. I'm just showing another question. It's only different because now the 1 is being subtracted. Or I could say negative 3x plus 1 equals 7. So now the 1 has gone back to being added, but the x is being multiplied by a negative 3 instead of a positive 3. Slightly different. And when you make these little changes, it makes the answer different. I could have negative 3x minus 1 equals 7. Now they're both negative. I could write them in the opposite order. I can write 1 plus 3x equals 7. And I think a lot of the supercharged students would look at that and say, well, that's really the same as the first one. And they would be right. And it will give the same answer, but it looks different. So when you are given a situation where you have to do algebra, it will always look different. There are so many different algebra situations that look slightly different from each other because we have different numbers and different ones have a negative sign. And all of these have more terms on the left side of the equals, but I could also have 3x equals 7 plus 1. And that could be the beginning of a problem. It's not necessarily as difficult a problem. It's not necessarily so much of a two-step problem, but see how easy it is to make all sorts of different questions just by changing one or two little things. That's the point of this. That's why I want to have a lot of practice. That's why I have 18 questions to practice with, all of which are two-step algebras, and I'm going to start doing it. So I'm not even going to answer this one because I need to erase anyway. I'll just put the first of the 18 that I put on my list over there up on the wall. I kind of like this. I can see all of the questions at once, and I can see them from here, so I don't have to carry a piece of paper the whole time the way I sometimes do. 15 equals negative 2 minus x. So this has a lot of negative signs. Well, it has 2, and the x is on the right side this time. And the number that's with x is also over on the right side. So it looks a little different, but it's not really different. And the order in which that we're going to solve it isn't, well, the order changes, but the process is not changing because I'm still saying the same thing. There's my x. I want it to be alone. It's not alone. It has a -2 with it, and it also has, it's being subtracted. So that almost looks like there's a -1 multiplied by my x, and that's actually the way I like to see it. The first thing I want to do again is I'm going to deal with this. I'm going to get it to the other side. Not really two-step. I was thinking that all of them are two-step. They're not all two-step. Okay, so I'm going to move that -2. I have to see this as a -2, a 2 that is being subtracted from my x. So I have to do the opposite. Notice how I'm leaving a space. This 2 is being subtracted, so I do the opposite, which is I add a 2. And then this minus x is still there. I just copy it down. If I'm adding a 2 on the right side, I have to add a 2 on the left side. These cancel. Now I have, and yes, it is a two-step. Now I'm realizing why. Now I have -x on the right side, and 15 plus 2 is 17, but I'm not finished. And that is actually a really good thing to happen, because it's something that happens to a lot of students where they get to this point in an algebra and they think they're finished because the x kind of looks alone, but it's not alone. It is being multiplied by a -1. That's my second step. When x is being multiplied by -1, how am I going to get x to be alone? I'm going to do the opposite. And the opposite of multiplying by -1 is dividing by -1. But I have to do that on both sides. This negative sign cancels with this -1. My x is now alone. 17 divided by -1 is equal to -17. My answer is x equals -17. Is there something funny about how I said that? Because people reading this would think -17 equals x. To make the point that x equals -17 and -17 equals x mean the same thing, which is why it doesn't matter if you isolate your x on the right side or on the left side. You have to isolate your variable on one side of the equals, and it can really be a matter of choice. A student who really doesn't like their x over on the right side can do more algebra steps and get it over to the left side. Now I'm going to erase and do another one. Let's see what the next one looks like. Not especially different, but there is something that's a little different. And we notice how much we're practicing our laws of signs, all of our knowledge about integers, positive and negative numbers. They happen a lot when we're dealing with algebra. So this one is -10 equals 4 minus x. Actually doesn't look especially different from the very first problem I put up today, but that was a one-step algebra. And is this a one-step algebra? No, and for the same reason as the previous example. Okay, what am I going to do? I'm going to isolate my x. I choose to isolate it on the right side because it's already there. So what am I going to do to do that? I'm going to get rid of this 4. Now this 4 isn't -4. So this 4 is being added to my x. And the opposite of addition is subtraction, so I will be subtracting a 4. The minus x gets copied down. Be careful, we have to copy down all of the minus x, not just the x. So this can't magically turn into a plus. It is minus x. If I'm subtracting a 4 on this side, I have to subtract 4 on the other side. That's the rule. These cancel. -x is isolated, but x isn't isolated yet. This is -14. I have to divide both sides by -1. My x is being multiplied by a -1. And because it has been multiplied by a -1, it's not alone yet. So I will divide both sides by -1. These cancel. X is isolated. -14 divided by -1 is equal to 14. So 2 steps. Doesn't take too much paper, but I'm going to do it again. And I am going to compare the 2 ways, but I'm not going to leave them both on the chalkboard wall at once. So what I'll do is I'm going to erase my answer, and I'm going to do this again. But this time I'm going to decide that I want my x to be on the left, just because some people really like having their x on the left. Sometimes I feel like having it on the left. Okay, so what am I going to do? It's still going to end up being 2 steps. But am I always only moving a number, like the 4 or the -10 from one side of the equals to the other in order to isolate my x? No, those are not the only things we can move. This term can also be moved. So, how will I do that? I'm subtracting the x. I want to do the opposite, which is adding an x. Let me try that. I'm leaving some space over here because I know what's coming. The 4 is staying there. I had minus x, but I want to do the opposite, which is to add an x. If I'm adding an x on the right side, I have to add an x on the left side. These cancel. Wow, I canceled my x. That's crazy. Then there's no x left in the problem. That's not true. Because of the fact that I had to also add an x on the left side, I still have an x in my problem. Now I have negative 10 plus x, I'll make that negative sign bigger, equals 4. Okay. Oops. Okay, Doug, slow down. Negative 10 plus x. I said it out loud correctly. I just didn't write it correctly. Equals 4. Okay. I want my x alone. I moved it to the other side, or I can see it seems like I moved it to the other side. I did my algebra so that my x is on the left side now. I think I better phrase it that way. But it's not alone because the negative 10 was already over there and it's still there. So what's the opposite of negative 10? Subtracting a 10? It's adding a 10. Negative 10 plus x equals 4. But I added a 10 over here, so I have to add a 10 on the other side. These cancel. My x is isolated. 4 plus 10 is equal to 14. It's the same answer. In the previous version of this example, I had 14 equals x. Now I have x equals 14. They mean the same thing. I wanted my x on the left side, and I made it happen by following the rules of algebra. Checking the time. I'm doing fine for time. Looking at my next example. Time to do some erasing. I'm going to do a stretch myself, actually. It's the shoulders. It's always in the shoulders, and I was thinking about that yesterday. I think when I get this need to stretch my shoulders while I'm doing math, why in the shoulders? I think because they're close to the brain, and my brain is getting a lot of exercise right now, even though it doesn't really show. It's on the inside, but the brain is getting a lot of exercise. There's a lot of things happening in there right now, and I guess the shoulders are close to that, so they're affected. Okay, what I'm going to do next is I'm going to go and get my fizzy water because I forgot to bring a can. But first I'm going to put up the problem, the next problem that I want to do. And I will allow the students to work on the problem on their own if they wish and see if people come up with the answer. Negative 2x minus 11 equals 2. Okay, by the time I get my microphone off, half of the Supercharged students will already be finished this problem, but that's fine. I'll be right back. And I'm back. Let's get the microphone back on. I think I'm going to try just putting this thing in my pocket instead of clipping it on. Like that, I have a zipper on this pocket. I can even pull the zipper up. And then it shouldn't fall off. And I have my can of fizzy water. What flavor is this? Cranberry ginger ale. There's no need for soda pop anymore because these fizzy waters come in all the flavors that soda pop has, traditionally been dominating. But this is 0 calorie. It's fizzy, which is good when you are breathing in chalk dust and talking too much. Okay, let's get back into the math. So everyone probably already has the answer. I'll take a look at the chat and see if there's plenty of answers there. When the same answer keeps on coming up over and over again, I have a feeling it's the right answer. Okay, so two-step algebra. My x has a negative 2 that is being multiplied by, and it also has an 11 that is being subtracted. I want to deal with both of those things, but I'm going to deal with the minus 11 first. So minus 2x I copy. I have minus 11. The opposite of subtracting an 11 is adding an 11, which I will do on both sides. And the chalk, little pieces of chalk go flying. These cancel. My x isn't isolated yet, but it's more isolated than it used to be. I'm getting there. 2 plus 11 equals 13. Uh-oh, this one is going to give me a decimal or a fraction as an answer, but we don't care. We're doing algebra. We already know how to deal with decimals and fractions, and improper fractions and mixed numbers and all of it. If my x is being multiplied by a -2, I want to isolate it. I will divide both sides by -2. These cancel. X is alone. 13 divided by -2, well, my favorite way to show this answer is to just say, well, it's -13/2, of course. Nothing wrong with this fraction. I like putting the negative sign in the top, but even written this way, there was nothing wrong. It was the correct answer. But it's up there in the clutter of the work that's still being done, so I still like to say the answer at the end. X equals -13/2. Perfectly good answer, which means x is equal to -6.5. Yep. Oops, negative. Yep. And it also means x is equal to -6.5. We can express it any of those ways, but this is not a decimal fraction percent lesson. This is an algebra lesson. Okay, so now I'm going to move on to the next example. And you see how they all look a little different. They're all kind of the same, but they're all kind of not the same. And to me, that just makes it fun. Eventually, Aurora will have time to make the puzzle book for the airport bookshop that's full of questions just like this, with a bit of white space on every page for you to do the work. And I'll be buying those books at the airport and at the train station. It's such a good idea. It has to happen. 10 minus 2x equals 4. Okay, so we have a -2 with our x again. It just looks a little different this time because it's the second term. And does it matter? No, because we don't want to think about it as it always has to be said the same way. We want to look at it as, okay, how is my x not alone? How can I make it alone? Okay, there are two things with it. There's a 10 with it, and there's this 2 minus 2. I want to get rid of the 10. So that 10, it's not a -10. That means that 10 is being added to my x. It is being added to the term that includes my x. So I want to do the opposite of adding a 10. I want to subtract a 10. And if I'm subtracting a 10 here, I have to subtract a 10 over here. These cancel. -2x is still there. 4 minus 10 is equal to -6. My x is being multiplied by a -2. I need to do the opposite. I will divide both sides by a -2. These cancel. X is alone. -6 divided by -2 is equal to +3. I know my integers. I know my laws of signs. I see a couple of questions there. I'm going to look at them as soon as I finish, although if someone's asking about this, maybe I shouldn't erase right away. Ooh, I like both of these questions. Okay, what I'll do is I'm going to read out the question, and then I'm going to create an example that does the thing that's in the question. Is there... I'm thinking the gears are turning. The thing is happening that makes my shoulder muscles sore. Let's see. One of the questions is, what happens, where am I looking there? What happens if there's a fraction instead of a whole number in front of the x? This is a perfectly good question. And that is going to happen in some of the examples I've already made, but I am going to put a little asterisk next to this example because I want to show it two different ways, because this question makes me want to do that. So let me just quickly write that. That's a good idea for when I get there, but I'm not quite there yet. So we'll wait for the answer to that question. It's going to be answered in today's lesson. The second question, what if there is nothing left on the right side of the equation? Seems to me I have an example that does that too. This is clever. The students may as well. Oh, and I see an answer that was typed in, which was the correct answer from an earlier question. It's as if the students are helping me to create my lesson plan. And that's a good sign. That means that the students and the teacher are on the same page. I like this. Okay, I'm going to answer both of those, but I'm going to wait until I get to them, because when things are a little bit more challenging, it's better to wait until later in the lesson. That's why I'm doing it this way. So I'm going to go back to my original plan and do a few more. And I think it's time for me to speed them up a little bit, though. When I think of the time that I have left and how many questions I have left, I think it's time to start doing a couple of them quickly. So I am going to do this. So -7 plus 2x equals 3. -7 plus 2x equals 3. I'm doing the same thing. I'm going to say all the same things. I'm just going to try to go quickly because I think the students are getting used to this and they have an idea of what to do. So I want to get rid of this -7. That's a 7 that's been subtracted from my x. The opposite of subtracting a 7 is adding a 7. So I'm adding a 7 to both sides. These cancel. 2x equals 3 plus 7 is 10. Now my x is being multiplied by a 2. I'm doing the opposite. I'm dividing both sides by a 2. X is equal to 10 divided by 2, which is 5. Okay, that was fast. Fast can be fun. Don't go fast until you're ready, but when you're ready, that can be fun. It's interesting to think about how quickly you can do some of these things. Okay, that one is done. How about 2x minus 5 equals 5? 2x minus 5 equals 5. I am having a 5 subtracted from my term that includes the x. So I'm doing the opposite. I am going to add a 5. 2x minus 5 plus 5 equals 5 plus 5. I added a 5 here. I add a 5 there. These cancel, but these don't. 2x is alone, but x is not alone yet. 5 plus 5 is equal to 10. It's interesting, there's 5s all over the place here. Now, the x being multiplied by a 2, I want to divide both sides by a 2 so that I can cancel these. My x is isolated, and 10 divided by 2 is yet another 5. That might be one of the most beautiful algebras I've ever seen. I should take a picture of it, except I don't have to because it's written down right here. I'm going to draw another asterisk next to it just because I'm so proud of it. Okay, 6x minus 10 equals, I'm afraid to say the whole problem out loud before I finish writing it down because I know how fast supercharged students can be, and they'll have the answer before I even finish writing the question, and that would be a shame. Or would it? No, it's not really a shame. 6x minus 10, and Doug is coyly still not saying that final number we need. We can't really get started until we know what I'm putting over here, and I'm putting a 26 over here. Ha! So I am subtracting a 10 from my term with the x. So I'm doing the opposite. I am adding a 10 to both sides. This is fun. I really do have a lot of fun when I do this. Minus 10 plus 10. Makes me think about that book in the airport, though. 6x equals 26 plus 10 is equal to 36. I am going to divide both sides by a 6 because my x is being multiplied by a 6, and the opposite is to divide by a 6. I am doing that on both sides, of course. These cancel. X is alone. 36 divided by 6 is equal to 6. I have my answer. What I was thinking is, the way I do this, the way I get when I'm doing this, you're familiar with this now. You've experienced the Doug classroom atmosphere. I get kind of excited. So I wonder if I would be sitting in a train seat or an airplane seat with a little book and a pencil doing these, and if I'd be jumping around and all excited and fidgeting, and everyone else on the plane would be saying, what is with this guy? What is with this guy? What's he so excited about? And then they wouldn't want me to notice them looking at me, but they would peek over. Oh, he's doing algebra. Oh, didn't expect that. Okay, next one. 4x plus 10 equals 30. Okay, I am adding a 10. I've had to put a few 10s in these examples. I'm adding a 10 to my term that includes x, so I'm doing the opposite and subtracting a 10, which I have to do on both sides. See how quickly and efficiently I can do it and even say it because I'm getting used to it, and I'm so used to it because I'm doing a lot of practice. These cancel. 4x equals 30 minus 10 is equal to 20. My x is being multiplied by a 4. I need to do the opposite and divide both sides by a 4. These cancel. X equals 20 divided by 4, which is 5. There's that lovely 5 again. Same answer, different question. Interesting. Okay, where am I now? I'm going to start sort of crossing these out so that I don't get mixed up and accidentally do the same one twice. No, I'm getting into what I call the giant fractions. It's not really the type of fraction that a student asked me about. Ooh. What if there's a fraction and a decimal in the same equation? Which one do we convert to? That's a great question. You convert to either you convert to whichever one you prefer, which is the answer I really want to give. So if you have a fraction and a decimal and you need them both, it's good to have two decimals or two fractions. I'd like them to both be the same, but you also have to watch out for, is there a reason that you should choose a fraction? Is there a reason you should choose a decimal? And to know that, you have to sort of read the question. Some questions put you in a position where they want a fraction at the end or they want a decimal at the end. So read the question, and if the question is not telling you which one to choose, I guess you get to choose. But I don't like the idea of having an answer that mixes fractions and decimals. It seems sloppy to me. So it makes me want to either say, okay, I want them all to be decimals or I want them all to be fractions. This happens to me a lot, actually. I'm in this particular situation this student asked about so often in my usual math teaching environment where I teach all different levels of math all at the same time in the same class, mixed together in the same classroom. Next one, x plus 5. We're getting into those giant fractions. X plus 5 with a big fraction bar under it over 2 equals 14. Did I copy that down correctly? Okay, so now this is a different style. I mean, when you think about it, especially to beginners, this looks like a completely different question than all the ones that we've been doing up until now. It's not all on one line the way all the others were. This giant fraction sort of gives us two levels. It's like looking at a two-story house when you were walking down a street where all the other houses were one story. Can we deal with that? Well, if you were walking down the street and all the houses were one story and you saw a two-story house, could you deal with it? I think you could. So the answer is yes. Yes, we can deal with this. What do we do? What do we do first is the sneaky, tricky thing. Do I deal with this 5 first or with the 2 first? I want to get both of them away from my x so it can be alone. The goal is still the same. Isolate the x, isolate the variable, not always an x. Which one do I get rid of first? Okay, I know I want to get rid of the 2 first. But I want to try doing this one twice to show it in more than one way, to try to justify why I think that I should get rid of the 2 first. So what I'm going to do is a lot of times the students will just show multiplying by a 2 right away, but I want to write this over again so that when I do that thing where I multiply by the 2 so I can cancel, it doesn't clutter up my question. So if this expression that includes an x is being divided by a 2, and I want to do the opposite, I will multiply this whole side by a 2. I'm multiplying this whole thing, but it is really one thing because it's a fraction. It's one fraction. And it's being multiplied by a 2, but I have to multiply both sides by a 2. These cancel. And now I don't need the giant fraction anymore. X plus 5 equals 14 times 2, which is 28. Now I have to do what we learned first in the very first one-step algebra problems. My x has a 5 added to it. I need to do the opposite, which is to subtract the 5. But I will do that from both sides. These cancel. X is isolated, making sure it still fits. 28 minus 5 is 23. We know the answer is 23. Let's try to remember that. Just taking a quick look at the chat, but I'm not missing anything lately. That's good. Trying to keep up with these questions. I like the student questions. That's part of it being interactive, and we're all doing this, not just everyone's watching the teacher do this. Okay, I'm going to do this again, but I'm going to show it differently. We have to get x equals 23 at the end, though. We know that's going to be the answer. So I will erase this, and I will show it slightly differently. I'm going to point out something to you about fractions that include variables, fractions like this one, that students don't always realize, and it can cause confusion. This expression that includes my x, which is being divided by a 2, if I choose to draw it all in one line instead of in 2 layers like the two-story house, I can. But I cannot write x plus 5 divided by 2 equals 14. This isn't going to work. Not exactly, because this gives the impression that only the 5 is being divided by a 2. But I can tell from up here, no, both the x and the 5 are being divided by 2. How do you show that when it's all in one line? We've seen this before. You put a bracket. So if someone wants to ask this question and they want it to be fair, if they want to write it all in one line, they have to put bracket. Because if they don't, they've turned it into a different question. And then we see the bracket and we realize, oh, okay, my expression including x is being divided by a 2. What do? I do the opposite. I multiply by 2. I multiply both sides by 2. These cancel. X plus 5 equals 28. We know what's going to happen. It ends up being the same. I showed it differently, but it ends up being the same. I think the first way that I erased is a little bit easier to see what you're doing. So I don't want to go out of my way to rewrite these so that I use the bracket and the divided by sign. I prefer it with the giant fraction myself. X plus 5 has to have a 5 subtracted from it so that I could isolate my x. 28 also has to have a 5 subtracted from it. This x is just a ghost of an x. These cancel. X is alone. 28 minus 5 is 23. We knew that was going to happen. The bottom of the question looks the same as it did the first time. Where am I now? So we're getting into the giant fractions. We need to do a couple more. We cannot only do one question like this and expect all of the students to remember what to do. We have to do a few, and we have to make them look slightly different from each other so that we can realize that the steps aren't really different, because the steps are to apply the rules of algebra. And I'm realizing all of a sudden that I was starting to talk faster and faster and faster, and I'm feeling out of breath. And that means it's time for me to stretch and have a sip of this fizzy water. You knew that was coming. You knew the was coming. Okay. 20 equals, oh, this looks completely different. 20 equals x minus 8 over 3, giant fraction. The x is on the right this time. The giant fraction is on the right this time. Otherwise, it's not very different from the previous question. My expression that includes the x is being divided by a 3, and I want to do the opposite. So I'm going to multiply that side by 3, but if I'm multiplying the right side by a 3, I have to multiply the left side by a 3. These cancel. X minus 8 is isolated, but x isn't. 3 times 20 is equal to 60. My x has an 8 being subtracted from it, so it has to have an 8 added. Do the opposite. The 60 also has to have an 8 added. Add an 8 on both sides. These cancel. X is isolated, and it is equal to 68. And x equals 68, and 68 equals x mean the same thing, but we knew that. That one is actually quite quick, even though it is, I have moved on to the giant fraction type of problems. And here's another one. Another giant fraction problem, but I promise you the question about a fraction instead of a whole number in front of the x, which isn't exactly the same as what I'm doing right now. I'm getting to that right after I do a couple more of these giant fraction problems. And the other question about what if there's nothing on one side of the equals, that's there too. It's in our future. It's not too far in our future. And I'm going to make sure, I'm looking at the clock right now, I'm going to make sure that I do have time to include it, even if I have to skip some other question. -5 equals -4 plus x over 3. Still a giant fraction. So it starts off with this negative sign. Does that make it harder? Not really. When I look at that expression, -4 plus x, I'm already getting used to the idea that that means the same thing as x minus 4. If I really wanted to, I could rewrite it as x minus 4. But I'm not going to rewrite it because I know I don't have to. If I apply the rules of algebra carefully, remembering, follow the rules. Do the opposite. What you do on one side, you do on the other side. Only do one thing at a time. That's a recommendation rather than a rule. Okay, my expression that includes x is divided by a 3. So I'm doing the opposite, which is to multiply by a 3. But if I'm multiplying the right side by a 3, I have to multiply the left side by a 3. Notice how I wrote -5 and then I multiplied by 3 this time instead of putting the brackets with the 3. Doesn't matter. -5 times 3 and 3 times -5 are the same thing. That's something that I know you already know. Okay, these cancel. Negative 4 plus x is isolated. Negative 5 times 3 is negative 15. And there are students who will be confused by a leading negative sign. That's what I like to call this. That side of the equation leads off with a negative sign right away. Is it a subtraction sign or is it a negative sign? It's both. There's a lot of overlap between subtraction and negative signs. But I know that my x is having a 4 subtracted from it. And the opposite of subtracting a 4 is adding a 4. If I'm adding a 4 over there, I have to add a 4 over here. These cancel. X is isolated. Negative 15 plus 4 is equal to negative 11. Remember your thermometer. Negative 15 degrees. It got 4 degrees warmer. Negative 11 degrees. The thermometer is like the number line turned on its side, and I like the thermometer for that. It helps to make it easier to know when you're right, when you're adding and subtracting with negative numbers. Okay, is there another giant fraction? Yes. Yes, there is another giant fraction. So I'm going to do it. It is the last one. Checking the time. I'm doing quite well for time, which is good because I have a couple of special ones up ahead and I don't want to rush through them too quickly. Okay. Negative 2 equals x, up there, minus 3 over 4, giant fraction. Okay, we know what to do. We must be getting used to this. The expression that includes the x is being divided by 4. I want to do the opposite. So I am going to multiply that side by a 4. I will multiply both sides by a 4 because I have to do on the left side what I do on the right side. These cancel. Oh, I put the bracket around the negative 2 instead of the 4. Does it matter? No. In the same way that 4 times negative 2 is equal to negative 2 times 4, 4 times negative 2 is equal to negative 2 times 4. Interesting. It is true. I'm going to erase it, though, because I don't want clutter. Okay. These canceled, so now I have just x minus 3 over here. 4 times negative 2 is negative 8. My x is having a 3 subtracted from it, so I am going to do the opposite and add a 3. But I am going to add a 3 to both sides. Look what I'm doing. If I forgot to leave that space, that doesn't matter. I can add a 3 by doing this. So long as I don't lose that negative sign that's with the 8. The 8 is a subtraction of 8. It's still a subtraction of 8. These cancel. X is isolated. 3 minus 8 is negative 5. I've been forgetting to verify. Let's do a verification. I'll do it here. Negative 2 equals negative 5 minus 3 over 4. I rewrote the whole thing, but I replaced the x with the negative 5. Now, negative 2 equals negative 5 minus 3 is negative 8. And yes, negative 8 divided by 4 is negative 2. I get negative 2 equals negative 2. I get whatever number. I don't care what number I get. So long as it's shown to be equal to itself, I know I verified. Verification is great because you have the power to do it yourself all the time. If you were in some sort of exam where you're not allowed to have access to anything, you are still able to verify. So when you're able to verify in math, which happens quite often, do it because it gives you confidence in your answers. And it feels good to know that you did something right instead of just hoping that you did it right. I love verification. Okay, now we're getting to one with a fraction. What happens if there's a fraction instead of a whole number in front of the x? Well, it's not really very different, but we'll do it. X over 3. So there's the fraction. I'm not going to write x over 3. I'm going to write, no, yes I am. X over 3. So let me write the whole question before I talk about it. Plus 2 equals negative 7. Copy that down correctly. Okay. I wrote the x inside the fraction. That's not exactly what the student said. The student said if there's a fraction instead of a whole number in front of the x. The point is to say that x over 3 is the same thing as 1/3 x. Here, we're writing our numerical coefficient of x separately from the variable. But the way we write it, we know that x is being multiplied by a third. Here, we're writing the variable inside, and we don't really need to show the 1, so we don't show it. But x is still being multiplied by a third. Wait, you're saying, no, x isn't being multiplied by a third. I'll write it bigger. X is being divided by 3. Why is he saying it's multiplied by a third? Because dividing by a 3 and multiplying by a third are the same thing. Aha. And that is a good little insight to have into your fractions that sort of demystifies fractions and makes people able to see that fractions are just numbers. And you can just treat them as numbers. So x over 3 plus 2 equals negative 7. I can write x over 3, or I can write 1/3 x. I'm going to erase this stuff. I'm going to finish the problem, and then I'm going to do it again. But first, I'm going to have a sip of my fizzy water. Okay. Cranberry ginger ale flavored fizzy water. Okay. What do? It's not really that different. I have an x that's being divided by a 3, or multiplied by a third, and also having a 2 added to it. What do I deal with first? I'm going to deal with the plus 2 first. And how do I deal with that? I'm adding a 2, so I do the opposite. I subtract a 2. Oops. Minus 2. I subtract a 2 from both sides. So interesting how, even though the situation seems different, the way I'm talking about solving it sounds the same. I need to get rid of a number so I can isolate my x. I see how that number is being combined with the x. This time it's addition. I do the opposite. It's subtraction. I do it on both sides. I keep saying this because that's really always what we do. These cancel. We have x over 3 equals negative 7 minus 2. Need more chalk. Okay. I can combine those, though. I should have combined them right away, I guess. X over 3 equals negative 7 minus 2 is negative 9. Now what am I going to do? My x is being divided by a 3. I'm going to read it that way instead of saying it's being multiplied by a third, because it looks like it's being divided by a 3. What's the opposite of dividing by a 3? Multiplying by a 3. So I will do that on both sides. These cancel. Will this fit? Yes. X equals negative 9 times 3, which is negative 27. I have my answer. Does it verify? Negative 27 divided by 3 will give negative 9. And negative 9 plus 2 is equal to negative 7. Negative 9 degrees on the thermometer, with it getting 2 degrees warmer, brings us to negative 7 degrees. Okay, so that works. But what if I write it the other way? What if I write the fraction beside the x instead of the x inside the fraction like this? Well, let's just do it. I will ask you to remember that the answer was negative 27. So I'm going to erase everything except the plus 2 equals negative 7 part. And I'm not going to write x over 3. I'm going to write 1/3 x. Okay, what do I do if I have an x that's being multiplied by a number, but you're also subtracting a number? We get rid of the one that's being, sorry, we're also adding a number. We get rid of the number that's being added first. So I'll just copy down 1/3 x. The opposite of adding a 2 is subtracting a 2, which I do on both sides. These cancel. Negative 7 minus 2 is negative 9. And now I'm seeing it differently. I'm not saying x is being divided by a 3. I'm saying x is being multiplied by a third. What's the opposite of multiplying by a third? You could say it's dividing by a third, but I think it's better to say the opposite of multiplying by a third is multiplying by 3/1, the same fraction upside down. Because we know from our fractions knowledge that when you multiply two fractions that have the same numbers, but one of them's upside down, the answer gives 1. 1/3 times 3 is equal to 1. 1/3 times 3/1 is equal to 1. 3 times 1 equals 3. 1 times 3 equals 3. That's a fractions lesson. We're doing algebra. Okay, but if I am multiplying the left side by 3/1, I have to multiply the right side by 3/1, or 3. I can write it as 3/1 or 3, whichever I prefer. These cancel. My x is isolated. -9, oh, it's fractions. It looks different. Well, it's not very different. I'll turn that into a fraction. -9 times 3 is -27. 1 times 1 equals 1. I don't have to write a 1 when it's in the denominator. It will make my negative sign bigger, though. X equals -27. It's the same answer. So how we express our fraction X combination, whether the X is inside the numerator or if the whole fraction is sort of beside the X, it really doesn't matter because the algebra tricks that we're learning work anyway. That's cool. We need to do more like this with fractions with the X, and that's a good thing because I have more. Take a quick look. Yes. Oh. 5 plus x over 4 equals -12. Here's my x. It's being divided by a 4 or multiplied by a quarter, whichever we prefer. But it also has this 5 that's being added to it, and I'm going to deal with the 5 first. The opposite of adding a 5 is subtracting a 5. There's no plus over here, but there's no minus over here. So that means the 5 is being added. Plus x over 4 has to be copied. Equals -12 has to be copied. I'm subtracting a 5 here, so I have to subtract a 5 there. These cancel. X over 4 is isolated. -12 minus 5 is -17. My x is being divided by a 4. So I'm going to do the opposite and multiply by a 4. See, I keep on saying it different ways, but I still keep on doing the same rules of algebra we've been doing all along. If I am multiplying the left side by a 4, I have to multiply the right side by a 4. So this could have been 4 over 1 times 1 over 4, but it really means the same thing. The 4s are canceling. My x is therefore isolated. -17 times 4, oh, well, that's outside of the multiplication tables, but -17 times 4 is -68. Is that going to verify? Well, we find out right away. -68 divided by 4, that would give -17. 5 plus -17 does give -12. It verifies. Dude, this is fun. And it's not really different. I may have been presenting it as if, okay, now we're going to do something really different. And it actually isn't very different. But all these little ways in which it can look different, we need to see all of them so that we can realize that our algebra techniques work, regardless of all these little details. You just patiently apply the rules of algebra and it works. That one, that's that one, okay. And checking the time, being careful. -10 is the beginning of my next problem. Just saying it out loud helps me to find it again when I go to look at the page. -10. Now I know I won't grab the wrong one. Equals x over 4 minus 2. It's starting to seem like the same old thing. I want to deal with this -2 first. That's a 2 that's being subtracted from my expression that includes x. If I'm subtracting a 2, I want to do the opposite, which is adding a 2, which I do to both sides. These cancel. X over 4 equals -10 plus 2 is -8. My x is being divided by a 4. So I will multiply both sides by a 4. These cancel. X is isolated. 4 times -8 is -32. -32 divided by 4 is -8, and -8 minus 2 is -10. It worked. It keeps on working. Isn't that interesting? It keeps on working. That's the -10 one. Okay, -3. Oh, here's one that's slightly different looking. Very slightly. -3 equals x over, are my eyes deceiving me? No, they are not. X over -2 minus 9. That's a little different. Not very. And I don't think I need to panic. What I do think I need to do is deal with this -9 first. So leaving a space, I'm subtracting a 9 from my fraction that includes x, so I do the opposite, which is to add 9, which I do to both sides. These cancel. X over -2 equals, a little more chalk, -3 plus 9 is +6. My x is being divided by a -2, and the opposite is multiplied by a -2. There's no reason to panic. I'm just going to multiply both sides by -2 because I'm doing the opposite. These cancel, including their signs. My x is isolated. -2 times 6 is equal to -12. It worked. -12, lots of negatives in this verification. -12 divided by -2 is equal to +6. And +6 minus 9 is indeed equal to -3. It works. Okay, carefully checking the time. Where are we here? I only have 2 more. But I did want to get to that one that allows us to talk about what the student asked. Okay, I'm seeing a new question. I want to answer it. So I will write my next question because I think my next question allows me to discuss this. -x/3. This time the negative sign's up in the numerator where we're more used to seeing it. +2 equals 6. We're going to deal with 2 first. I keep saying that. And the student is saying, how do we know when to deal with the denominator first or the whole number to be moved to the other side? I like to say that this is further from the x. This denominator is more tangled up with the x. So it's kind of like if you had some sort of a long, well, it's kind of like this microphone cord. When it's tangled up, when you want to unravel it, the part that's the most tangly, you kind of have to save that for last. That's my creative little answer to this question. And if Aurora wants to add an answer to that question, that is fine, because I think there's more than one way of answering that question. But anyway, that's the way I like to see it. If this 2 is over here, further from the x, I'm going to move it out of the way first so that this mess doesn't seem like as big a mess because it won't have as much stuff around it. So finishing this problem, because it was the next problem, I'm adding a 2 to this fraction that has the x, so I'm going to do the opposite, which is to subtract the 2, which I will subtract from both sides. These cancel. -x/3 equals 6 minus 2, which is 4. Now, this is turning into a 3-step, but it depends on how I want to show it. I can say my x is being multiplied by -1/3 and divide both sides by -1/3 if I want. What I can also say is I'm going to multiply, my expression that includes x, my negative x, is being divided by a 3. So I'm going to multiply both sides by a 3. These cancel. My negative x is isolated, but that doesn't mean my x is isolated, which means I'm not finished. 4 times 3 is 12. And I still have to, remember we saw some of these way at the beginning. I still want to get rid of this negative sign. My x isn't really alone. If it has a -1, be multiplied by it. So I'll divide both sides by -1. These cancel. X is equal to -12. We got our answer, and it ended up being a 3-step. Okay. Now, the last one on my list, which might be the last one, it depends on how long I end up talking about it. I am going to change my chalk because that one's just getting too short. Okay. I need my eraser cloth. That's why I walked over here. Okay. What if there's nothing on one side of the equal sign? I have to look way back up. But nothing left on the right side of the equation. Now, that could also be what if there's nothing left on the left side of the equation, because it could happen on either side. 4 minus x/4 equals 4. Okay, so it doesn't look very different from the ones we've been doing, so we may as well just go ahead and work on it the way we have been doing. This is too tangly, so I'm going to deal with this 4. even though there's a minus sign after the 4 itself is positive. That means that's a 4 that's being added to my stuff with the x. So the opposite of adding a 4 is subtracting a 4. This I'm copying down. If I'm subtracting a 4 here, I have to subtract the 4 there. These cancel. Minus x over 4 equals, these canceled, which means there's a 0. Oh, so there is nothing left on the right side of the equals, exactly the way the student said. But nothing is 0 in math. So there's a 0 there. It's still a number. It's 0. What will we do? I am going to multiply both sides by 4 so that I can start making my x be more alone. And I'm doing it in several steps the way I did last time. If I'm multiplying the left side by 4, I have to multiply the right side by 4. These cancel. Negative x is isolated. I'm not finished. Oh, 0 times 4 is equal to 0. And now my x is being multiplied by a negative 1. I'm not finished. I want to finish. I'm not finished until my x is isolated. Do I have room? Yes, I do. I will divide both sides by negative 1. These cancel. X is isolated. 0 divided by negative 1. Just like 0 as a numerator in any fraction is equal to 0. It means x equals 0. It means my answer was x equals 0. But we know that in math, sometimes the answer is 0. Those who know Doug very well realize that in fractions, for instance, there's a lot of pizza. And when you have pizza and Doug, the end result eventually is that there will be 0 pizza. Here I am thinking about pizza again, and it's the algebra lesson. X equals 0. Will it verify? 4 minus 0 over 4 equals 4. I've rewritten this so that I have a 0 in the position where the x was. But 0 over 4 is just equal to 0. And 4 minus 0 is equal to 4. It verified. It works. So the fact that there was nothing on the right side of the equation was because there was a 0 on the right side of the equation. And whether you want to argue about whether 0 is nothing or not, well, that's an argument that can go on forever, because 0 kind of is nothing, but it kind of isn't nothing at the same time, because 0 is also a number, and a number that's perfectly useful for nearly all mathematical situations. There are times when a 0 can be inconvenient in math, but this algebra isn't one of those times. So I had a 0, and I said, oh, well, that's a number. I'm used to doing algebra with numbers. I'm just going to keep on doing my algebra. And I didn't quite get to the end of my hour, but okay, there are a couple of new questions. So with the very small amount of time I have left, I might be able to answer them. Will you ever have a percent in front of the x? Well, I don't want to say it's not allowed, but I am casting around in my vast experience of teaching math from so many different levels, so many different units of math topics, the geometry and the decimal and percent math. And I'm trying to remember if I've ever seen this before, and I don't remember ever seeing it before. So maybe the answer is no. Will you ever have a percent? Certainly not in one of these algebra questions anyway. You're not going to see me giving you an algebra question where I throw that in, because that sounds like a trick question to me. From Aurora. Oh, let me read this properly. Oh, okay. So I am going to give you a message from Aurora. Your next step after the practice that we've done today is to do the workbook that is called Equations. And if you need help with that, Aurora has videos that will help on the website. So that is really good news, because that workbook sounds like, well, actually that workbook sounds like the book I wish I could buy in the airport bookstore. Maybe Aurora has already written these books. And we are really getting very close to the end of the hour, so I will not try to make a new question. What I will do is say goodbye and say thank you. The Supercharged students are a joy to teach at all times. My brain feels healthier and smarter. It needs a bit of rest, but it feels better now. Thank you very much. You guys do that to me all the time. I will see you next week. A goodbye from me and my beautiful assistant Mocha, who is upstairs. And at this point, I'm going to stop talking, but I will keep on waving and looking at the chat in case anyone's typing anything. Oh, and if you still have questions, you can email me at doug@superchargedscience.com. Don't forget, you can always do that.